From an airfield in Northern California flies a most unusual aircraft. It's a converted C-141 cargo plane, and it carries a telescope. This is the Kuiper Airborne Observatory, run by NASA from the Ames Research Center. The main enemy of the astronomer is the Earth's atmosphere, which is dirty and unsteady and cuts out many of the important radiations coming in from space. Obviously, going up a mountain helps, but there's still a great deal of atmosphere left above you. And short of going into space, as the Hubble Space Telescope has done, the only real answer is to use an aircraft. The telescope of the KAO is a 36-inch reflector carried in front of the aircraft's left wing. The aircraft itself can fly at 41,000 feet. That's above 85% of the Earth's atmosphere and above 99% of the water vapor, which is particularly important. First of all, why is it called the Kuiper?
It's named after Gerard Kuiper, a Dutch astronomer who moved to the United States, well-known planetary astronomer, who was the first to use airborne techniques for infrared astronomy.
What range does the plane have?
I know the range really in terms of time rather than distance. The maximum length of time the airplane can fly is 12 hours, but we never fly that long. You need to have some reserve. And the longest flight was the one for the Uranus occultation in 1977 at 10¼ hours.
Could you say something about the design of the telescope itself?
The telescope is a Cassegrain telescope. The light comes through the side of the airplane off the primary and secondary mirrors, but then it's deflected off to the side by a flat mirror and goes through a hole in the wall of the telescope cavity so that the instruments can be located in the aircraft's cabin at a comfortable environment.
What about navigation? How do you keep the telescope pointed accurately?
Well, for pointing at a star in the sky as with a moving platform, as the stars move across the sky, the airplane has to turn so that the telescope is always pointing at the star, and that means its flight path has to be curved. So our flight plans look very peculiar to flight controllers. The telescope is kept pointing steadily by 3 separate systems. The first is a vibration isolation system that's essentially shock absorbers. The second is to keep it pointed at the star as the airplane is rolling and yawing. The telescope is mounted on a spherical bearing on a thin film of air, and there's a gyro-stabilized system for keeping it pointed the right direction. And then thirdly, there's an optical tracking system.
Obvious advantages over ground-based astronomy because they're above so much of the atmosphere. But it's fair to say that there are also some advantages over a space telescope.
Well, the main advantage, I think, is that we're able to fly an instrument and modify it and fly it again and modify it and build a new instrument and fly that in a way that you can't with a spacecraft. And we have access to the instrument in flight. So our instruments tend to be at the state of the art, and we can be a little riskier with our instruments than is possible with the spacecraft.
In a few hours' time, we're going to go on an observing flight with one of the Kuiper astronomers. Now, bear in mind that every flight is different, and each one needs different instruments, and they have to be installed, and that is going on now. A great deal of work has to be done before each flight. Also, the interior doesn't look very much like a conventional aircraft, does it? Bear in mind also, it's going to be extremely noisy, and therefore we're going to have to wear ear protectors. Could you tell us just what you're going to be doing on tonight's flight?
What we're planning to do is to establish infrared flux standards, spectral flux standards, for use by space satellites working in the infrared, and also for the Kuiper Observatory itself.
What instrumentation will you be using?
We're going to be using an infrared spectrometer. It's sensitive from 3 to 30 microns and has a spectral resolving power on the order of 200. This instrument needs to be calibrated accurately because we're trying to establish stars for use as standards. The stars then can be used by space observatories like ISO. To get the instrument properly calibrated, though, we have to look at a standard that we know very well. This black body source emits a very well-known flux versus wavelength radiation. In order to duplicate the conditions of flight, however, we actually run this radiation through this cold chamber through some optics which simulate the telescope optics in the airplane and through a cold cavity that's at the temperature of the telescope in the sky. And that way we get our infrared spectrometer properly calibrated.
Just how valuable is the KAO for your work?
It's absolutely indispensable because so much of that 3 to 30 micron band is absorbed in the atmosphere by water vapor. So the KAO gets us to 41,000 feet, where we're above over 99% of the water in the atmosphere. As a result, we can see the radiation coming from stars in the infrared in the regions that would have been absorbed by water.
So this work can't be done with a conventional ground-based telescope?
No, it can't.
Are there any great advantages to your being up there on the flight with the instruments?
The advantage is that we don't have to make the instruments completely automated, so that we can be there to operate the valves and the knobs. Also, if anything unexpected happens, we can make adjustments that you wouldn't be able to make in a completely automated experiment, where you really do have to anticipate everything.
Are there any major disadvantages?
Well, I guess a disadvantage is simply that you have to be up all night with it, and the discomfort, and it requires a larger crew for a manned airplane, but airplanes are going to have some kind of a crew anyway. But disadvantages are also that it has to be made for the vibration environment of the airplane. Well, really minor compared. It's no worse than going to a ground-based observatory on a mountaintop. The vibration problem is just as bad, especially if you have to drive your instrument up on a dirt road.
An hour before takeoff, there's a full briefing for everyone going on the flight.
I'd like to talk about, looks like another one of our good old 7.5 hour, lots of turns, long northbound leg. The winds look pretty calm. Trope height's real high down in the southern part.
We'll be below it.
Is that going to be a problem? Or?
Well, yeah, we'll just have to correct for the water.
I guess you've all seen the safety video. If there's any kind of problem like a rapid decompression, or you smell any smoke, or we have a fire, the first thing you want to do is get on your oxygen mask. And if you didn't pick it up, make sure you get it before you go. Also, stow all your loose belongings here before we take off so that it doesn't bounce around. Try and keep the plane clean here.
So with everything safely stowed on board, including essentials like midnight snacks, we took off on our night tour of America. While the cities far below us slept, we watched and listened on the intercom as the astronomers went through their observations, while the support crews kept the plane on its precise flight plan.
So you started this quad.
Okay, what is this? Second?
Third quad.
The
Just
third
switched.
quad, okay, good.
And Jesse's pulling it in.
Time left?
28 minutes.
Thank you.
Okay,
We're climbing up to 41,000, by the way.
Okay. Okay, did you, what's the number?
How the airplane's moving around the telescope?
we're on
3,
1
4, 5,
This is what the motion is on the...
Just the fourth
This
quad
guy's
coming
not
in.
moving
Right.
at all.
Switch to positive. Integrating.
Diane,
Yes.
you're recording dot B and dot M, right?
Yes.
Yeah.
Good. Okay.
Fred, you can start turning. We're just going to look at the sun buffer.
Not yet. Not yet. Yeah, we've got to get coordinated on this. I'm gonna...
It's good. Go.
Okay, Polly in, please.
Polly's in.
Do we confirm the filter, Fred? 1015?
Point five.
Yeah, it's
Okay.
1015.5.
Thanks.
And pressure is 760.
Thank you.
How we're doing now, then? Just 3 quarters?
12 minutes.
Thank you. It's a nice overlap down here.
Yeah.
It's a good scheme.
Okay, integrating, right beam.
What do we know? This is the end of the second?
Yes.
Okay, at the end of the second, we'll get a time lapse and see.
What are the graphs and monitors telling you about how you achieve the standards?
Well, throughout the flight, we're monitoring the data as we take it, and what the graphs show is what our signal to noise is. So they'll show us how big our errors are. As we accumulate the data, we see the errors go down.
What have conditions been like?
The conditions in this flight have been quite good. It's been a smooth flight. Most of the equipment has been working very well. It's all been working well enough to take good data so far.
Any unexpected results or just satisfactory routine?
It's really been what we expected. We're doing standard stars, and so it's not unusual that there wouldn't be any surprises.
You have a large crew here. How vital are they to the success of the operation?
They're all very important, and it starts with the pilots in the front who are guiding the plane and keeping it stable, even though we're at 41,000 feet, where it's pretty hard to do that. We have a very well-trained crew of telescope operators with a lot of experience. It's a complicated system because it's stabilized by gyros and feedback from the star image. The tracking acquisition is a tricky job. It's computer controlled, but there's manual interaction. It's very important that all these people are working together and doing everything right.
The KAO has the great advantage of operating at an altitude far above that of the highest ground-based observatory. And of course, it can be in the right place at the right time. And although the telescope is not really big by modern standards, it's still powerful enough to be used for all branches of research when operating under these near-ideal conditions. The KAO was a very bold idea. Do you think it's really come up to expectations?
Well, I have to admit I'm biased, but I think it's done much better than people expected at the time, mainly because of the phenomenal improvements in infrared detectors over the last 20 years.
What would you say have been the main scientific achievements of the KAO?
Well, they range over a wide variety of fields. In the planetary astronomy area, they include observations of water on Jupiter and Mars, and in comets, and in the area of star formation, measurements of magnetic fields in star-forming regions, and observations of spectral lines formed in star-forming regions and in shock waves that are associated with them.
There have been major discoveries. I'm thinking, of course, about the rings of Uranus.
Well, I was a graduate student on that flight, in fact. It happened quite by accident, but because of the KAO's ability to move, we were able to be in the optimal place for the occultation, and were able to deduce what was going on.
What about the atmosphere of Pluto?
Well, that was an occultation that occurred in 1988, and the predicted track of the occultation unexpectedly moved towards the end of the period before the occultation, but we were able to follow it with the airplane and be in the right place at the right time. It has a very unusual atmosphere, like none that we've seen before.
Then, of course, there's Halley's Comet.
Yes, the KAO was dispatched to New Zealand to do flights in support of the Halley Watch, and that was where water was first discovered in comets.
It's planned to replace the KAO with another plane. It'll be a converted 747. The project is to be called SOFIA, the Stratospheric Observatory for Infrared Astronomy. How will the Boeing 747 be adapted, apart from having a hole cut in it?
Well, there's a lot goes into making a modification like this. There will be a big pressure bulkhead installed in which the telescope will be mounted, which will separate the operating area for the scientists and the crew from the telescope. The telescope looks through an open port, and so that back end of the airplane will be completely depressurized. So there's a big bulkhead that goes in. There are facilities for the telescope which have to be installed. an improved power distribution system and so on. And of course there are the structural modifications that go around the hull to retain the original stiffness and strength of the fuselage.
What are going to be the main advantages of SOFIA over the Kuiper? Not altitude, I gather.
No, it's not altitude. It's the size of the telescope. You know, our ground-based colleagues are very excited about building telescopes that are a factor of 2 larger in diameter than the existing ground-based telescopes. And SOFIA's telescope will be a factor of 3 bigger than the existing Kuiper telescope.
What kind of telescope will it be?
It will be 2.5 meters or about 100 inches in diameter. The primary mirror, that's the collecting area, that provides us the additional sensitivity and improved clarity of the images that we'll get.
One thing strikes me. In the Kuiper, the telescope is mounted in the front of the aircraft. In the SOFIA, it's at the back. Why is that?
Well, it's just a matter of economy. You know, it's a lot cheaper to fly in the coach than in the first class section of a Boeing 747. Well, we have the same effect here in installing a telescope in the back of the airplane. There are fewer disturbed systems. The fuselage is practically round, which makes the door mechanism much simpler. We only need 1 pressure bulkhead instead of 2. Practically every engineering consideration suggests that you're better off putting it in the back instead of the front for cost reasons.
What about the instrumentation?
Well, the instrumentation is of a tremendous variety because the telescope covers a wavelength range from about 0.3 of a micron, that's the ultraviolet side of the visible part of the spectrum, clear out to 1.6 millimeters. That includes the entire near-infrared, mid-infrared, and far-infrared and sub-millimeter parts of the spectrum. So you need a wide range of instruments in order to cover all those wavelengths.
What about some of the main subjects you're going to study?
Well, again, there will be a very wide range of subjects because of the long wavelength range and the different instruments. But star formation will be one of the principal topics that we study, and that's because stars are formed in clouds that are so opaque because of the dust particles in them that we cannot see there with ultraviolet or visible light. But the infrared is able to penetrate, and so we can see inside these dark regions of our galaxy and in other galaxies to study how stars actually form by the collapse of segments of the clouds, and permit us to look at the very earliest stages of the formation of stars.
And one very important point, when do you expect SOFIA to be operating?
Well, we hope to have SOFIA operating by the end of the year 2000 if our current plans for development are on schedule.
The KAO has been a great success. SOFIA will come next. But undoubtedly, the KAO is going to be remembered as having shown that airborne astronomy can play a major role in modern scientific research.